Good afternoon.
Hey, how's it going?
It's going. Short weekends like always.
Well, one more week and we have a spring break next week.
More work. Whoa, man. I always get confused between this class and finite elements.
uh,
Like I was about to ask you, did you finish grading the exams? But I'm like, wait, this is that's tomorrow.
yeah, I haven't started. I still haven't started looking at those ones yet, but so probably the finite element exams I'll have it done by Thursday.
Nice. Uh, I
Usually
guess.
usually I do 1 week, so I grade the exams after about 1 week of um, afterwards.
So during your spring break, that's you should not work during your spring break. You work a lot.
Well, it's inevitable sometimes. I mean, I know you guys. I mean, I at least try to not give you anything to work on spring break, but I know for other classes you guys have a lot to work on, so um,
Yeah.
it just happens.
Some professors aren't as nice as you.
I've heard. I think this was more last semester during Thanksgiving. I've heard some professors had lectures during Thanksgiving week too, which is
Really?
it wasn't that many. It was maybe just like one or two, but yeah, that's kind of what I heard.
That sucks.
Yeah.
Imagine. You over here eating your Thanksgiving dinner and watching your professor lecture. Oh, that'd be funny. Oh man.
Uh, it's always hard for me to work during March Madness season too.
Oh,
I'm watching a lot of the games.
you're not split screen?
No, no. I mean, especially not during the lectures. No, I can't watch the games during the lectures. Um,
Halfway through the lecture, you're like, wait, hold on.
yeah,
All right.
my alma mater's doing really well too. UCLA, they've been winning a lot. So it's
Yeah.
their third. They got their third win today, and they're on to the Sweet 16.
Jeez. I think after my senior year of high school, I kind of just like veered off of sports.
Mm.
But yeah, you gotta pay bills. You gotta pay attention in class now. I don't know how some people do it.
Last class, I had someone told me he was hungover from watching college basketball and drinking over the weekend.
Oh man, that must have been a crazy game.
It must have been, yeah.
Mm. Crap.
Hi, Sasha. I'm good. Yeah, I'm ready for spring break. I'm sure you guys are too. Yeah, it doesn't matter. So I know in the fall semester, the Thanksgiving break takes place a little bit later, but always like the week before break is always the hardest week to get through, just because I think just because your mind is expecting the break, and then and then you kind of take off. And oh man, you have the exam on Wednesday. That's tough. But at least it's before the spring break, and then after, and then so during the spring break, you don't have to worry about anything, relatively speaking. Not an exam anyway. Oh man, oh, that's tough. Yeah, but I mean, yeah, at least it's before the spring break. But yeah, study guides. I've talked with other people about study guides. It seems like not that many people do that. Actually, when I was in college too, the professors hardly gave study guides as well, and so we kind of had to make them on our own. um, or in like it was a lot more common for my classes to have TAs too, and so usually the professors left it up to the TAs to either produce a study guide or not. And with TAs, there's a very wide range of like TAs that obviously want to be there, that that like teaching and like what they do, within other TAs that are obviously just like I need this to get paid and I want to spend the least amount of effort possible on it. Oh, he said oh, that's not good. If he said he would give you one, he should give you one. Yeah. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Besides studying for exams, seems like quite a few classes have exams this week. That's good. That's good. Yeah, one more week and then we're on spring break, and so I know you guys are probably looking forward to it a lot, or maybe not. Maybe probably a lot of other professors can assign you a lot of stuff to do over spring break, but at least you don't have classes, and at least if you have a little bit of time to relax and at least sleep in or something, right? So I'm definitely looking forward to spring break, because it's definitely my time to usually catch up on work and wake up a little bit later than what I usually do. Okay, and so the plan for today is that we're going to continue on with our lecture notes on you know on finite volume methods. So I think we're just introducing it, and so we're going to continue on with that. But the first thing I wanted to go over today is the project. And so I finally, got everything squared away for the project, and so I wanted to talk about it with you guys. Talk about it with you guys, just so that if you want to get started on it, you can. Because actually, technically, if you want to do the project with finite differences, you have everything that you need to do it. And so basically, I posted up the project specs as well as the starter code onto Canvas, so you can start to take a look at that if you want. But I think probably the most important thing that I want to say before we get started is the due date. And so the due date for the final project for this class, I usually for final projects I have some intermediate due dates, but for this class, since most of the work is going to be on developing the code, I only just have one deadline for this, and that's when basically all the deliverables are due. And so all the deliverables for the final project will be due Sunday, May 23rd. Okay. And the time for the due date is going to be 11:59 p.m. as usual. And so if you want to track that relative to the week number and the finals week number, this is basically the Sunday after finals week. And so just from my perspective, they usually give me a week after the finals week. So they give me up until basically the Friday after finals week to finish grading all the exam or all my things and put final grades in. And so basically this is kind of the last date that I can have it due to give me enough time to grade it, because I have final projects for your class and also final projects for two other classes I need to grade too. So I have them all due on the same day. So during that week, after the 23rd, I basically just have a grading flurry up until Friday just to try to get everything done in time. So this is kind of as far back as I can push it, just to make sure I still have enough time to grade. But I try to make it, I try to give it after the finals week, because I know a lot of you guys have final exams during that week. I know a lot of you guys are seniors too. You guys probably are really busy with senior design during that week as well. So I try to give you a little bit of flexibility after that week to kind of finish up the writing, finish up the code in order to get it in. Okay. And so so for the first part of class today, probably for the first 15 minutes, I'll go over the specs with you. Basically generally what you can kind of expect. And I'll show you where you can find all the files onto Canvas as well. Before I do that, are there any questions I can answer before we get started?
Do you know what day we're gonna have midterm 2?
Midterm 2, let me see.
Because I know it says it's like week 13.
Yes, it should be the Wednesday of week 13. That's what I planned. And so I'm not sure what exact date that is. So let's see. Next week is spring break. 37 should be April 21st for the second midterm. Let me double check that with the syllabus just to make sure. Yeah, there haven't been any changes in plans. Yes, Wednesday, April 21st.
Thank you.
Yeah, that's the plan. But I've in the past I've pushed exams back before if the week ends up being pretty busy for everyone. So if it gets closer and you guys are having kind of a crazy week, just let me know. And then I can always push the exam back. I'm always okay with that. But just let me know earlier, just so we can kind of plan for it. Okay, and so let's talk about the final project. So let me go ahead and share my screen. All right, and so just like we mentioned last week, the idea for the final project is to have you guys simulate a gas leak. Okay. And so here's like my, MS Paint, or actually in this case, MS PowerPoint rendition of a gas leak in a square room. And so I basically just Googled gas leak and I got this JPEG and I pasted it into a square. And then that is basically the situation that you're going to simulate. I tried to find a better picture, but a lot of the pictures end up just being not really what I wanted. So I kind of made my own on the fly. So use your imagination of what it actually is. Okay, and so I think everyone here is familiar with gas leaks, and so they're incredibly dangerous, as the fumes not only are toxic to breathe in, but if you try to light a cigarette or something inside a room with a gas leak, you will have a very fiery, so it's not a good thing. And so residences and utility companies, they're constantly trying to monitor gas leaks, and they want you to report these as much as possible. So it's something, it's something of a real engineering interest and something that we can model with the methods that we do in the class. So that's why I thought, it's a kind of a good topic for the final project. Okay. And just like everything that we've been doing in this class, it follows the same convection, diffusion, conservation equation. And so we have all of our terms in here. And so we have our unsteady term, we have our convection terms, we have our diffusion terms, and also a source here as well. And so the source actually takes a physical meaning here, and the source is actually going to represent the gas leak that's going to happen. Okay. Right. And what's going to be unique about this is that things are and what's going to be unique about this project that you haven't probably done in your homeworks yet is that different events are going to be triggered at different times in the in the simulation. And so basically in the code you'll see that in the starter code too, that I have you write a lot of if statements to have certain events trigger at certain times, and that actually creates like a really interesting kind of phenomenon. And so I'll show you kind of the the ending result. And so under the default set of parameters, this is basically what you can expect from your simulation. And so in this beginning stage, basically you have a leak that's happening, kind of near the middle bottom of the room. And at a certain point, you're going to open up a window on this side, and the window is going to blow air out of the room, which is going to take some of the gas with it. Okay. And then at a second point, if you kind of notice near the tail end of the simulation, another window is going to open on the bottom section of the domain, and that's going to push air down too. So like right there, you can see kind of the second window opens and it takes some of the gas with it. Okay. And so of course, as you know, this is a very irresponsible way to deal with the gas leak, because if you have a gas leak in your room, you don't want to just open up your window and just have the gas leak out into the environment. And so, your neighbors probably wouldn't be happy with that. But just for kind of the tools that we have in this class, that's something that we can kind of easily do. Question. So how fast does the air move? Oh, it's a good question. So that's something you can actually modify in the script as well. And so the airspeed is going to depend on whatever you set your convection velocities here. Okay? And so I have a default set of parameters that basically give you the animation that I've shown you there. But part of the project is actually, once you have everything implemented, you can go in and you can modify some of the values of some of these parameters and see how they affect your results. And that's going to be a big part of your final report too, is not only simulating just the default set, but also what happens when you change the convection velocity, what happens when you change the diffusion parameter, and seeing how that affects your results. Okay, and so here's your domain, right? And so it's going to be a 2D simulation, obviously, and the simulation is going to start out with a zero flux boundary condition on all sides. Okay, and so you can see we have Neumann boundary conditions all around, and the Neumann boundary conditions are set to 0. And so what this simulates basically is that there's no way for the gas to escape from the roof, right? And so that's why you have all of these things at 0. But at different times during the simulation, you're going to change these boundary conditions, to basically simulate a window being opened on certain areas. Okay, but this is your starting domain. So starting out, you're just going to have basically simple Neumann boundary conditions set to 0 on all sides, and you have basically our same square domain. Okay. Right, and so here's some screenshots about what you can expect. And so basically at peak danger, and so basically when the gas is leaked for about 1 second of simulation time, you're gonna get this distribution here. And then after the first window opens, you can see that a lot of the gas is kind of flowing out. And then after the second window opens, that drives more gas flow out there. Okay. All right, so let's talk about the requirements. And so basically, a lot of the requirements for this project are going to be in actually writing the code. Okay? And so up to this point, we finished covering the finite difference method. And so, you can absolutely implement the project using finite difference. And so actually, technically, if you want to do this project with finite difference, you actually have everything you need to implement it. And so, you don't have to wait for anything more in the class. Or, the other option that you have is you can use the second method that we're going over, which is called the finite volume method to do this project. Right? And so if you're an undergraduate in this class, you actually have an option. So you can either do finite difference or finite volume, depending on whichever one you find easier. Okay. But if you're a graduate student, or if you're an undergrad and you're taking for graduate credit, you don't have an option. So you kind of have to do both. Yes. Okay. So yes, grad students have to submit 2 codes. It sounds like it's double the work, but once you figure out one, then it's a lot easier to kind of transfer that to the second code. Yeah. I'm not going to tell you which one's easier because because then obviously everyone's going to do the easier one. So I would say listen to how the finite volume method goes over the next couple of weeks, and then kind of use that to help you decide what you think is easier. Because for some people, finite differences kind of just makes more intuitive sense to them. But I would say, finite volume actually has more physical, intuitive sense, just in terms of how the equations are formulated. And so, in the end, you get the same thing. In the end, you're going to get the same, it's the exact same phenomenon. It's just kind of implemented in different ways. And so I would say, just kind of, listen to how the finite volume method is going if you want to wait for that. But if you already feel really comfortable with finite difference, I would say, go for that as well. And so just kind of see how it goes and see which one you find better. Okay. They're both good. Okay, so they're both going to give you the same thing. So from my perspective, I think for me both were kind of equal. But I've known both of these methods for years now. So I'm not the fair person to ask about these things. Okay, and so since a big part of this is going to be writing your MATLAB code, I would highly suggest you guys to go over, all the example codes that we've done in the class, all the homework scripts that we've written, because, the project can build off these guys. And so, I'm not introducing anything drastically new just for this project. And so it's kind of like, we're using kind of the same script that we've been working with in class, just kind of applying them in a different way. And so, I know I'm providing you guys the starter code, but, look at, the way that we've done like implicit Euler methods, from the lectures and in the homeworks. Look at how we've done convection field. Look at how we've done diffusion in 2D, from our previous scripts, and use that as kind of, your references to help you implement this one as well. Because even though, there's a little bit more on top of this, on this project code compared to what we've done before, at its heart, it's still, still our same unsteady convection diffusion codes. Yeah. All right, when do you think you should start on this? So if you want to do finite differences, you want to take a stab at it with finite differences, you can start it right now, actually, because we've covered basically everything that you need to with finite differences. Minus one smaller topic that we'll cover, kind of near the end of the class, but you can do 95% of the code already. You can actually get this method, this result right here. And so, actually this result right here I did with kind of the basic, all the basic schemes that we've gone over already in the class. And so you can already get this if you want. And so if you want to start this, I guess probably after your midterms. So if you want to start this over spring break, I would say go ahead and take a stab at it. Can you copy and paste 95% of the code already? Well, I mean, it depends on kind of what you you say about it. But a lot of it can be used from before. Yes. There will be a lot of differences on the time gating stuff. And so basically, I basically kind of summarize all the additional things that you need to do on top of what we've done before, right? And so, outside of these 3 points here, everything that you can, everything that we've done before, you can kind of copy and paste. But you have to copy and paste it in the right places, and you have to use them in the right places. So, you can, a lot of the code is reused, but how you use it, I think, is going to be the difficult thing. Yeah. I understand. The copy and paste off your own work. That's okay. Okay, and so compared to like a normal script that what we're doing, here are kind of the 3 new things that you need to do. Okay, and so the first new thing that you need to do is to implement what I call a spatially dependent source term. Okay, and so we've done examples where we've had source terms before. So we've had this Q of X, but I don't want you to simulate a case where the gas is leaking from everywhere in your room, because that would be terrible. And so I basically want you to localize your gasket to just one small region of your domain. And so that's something we haven't done before. And so what you're going to do is you're going to implement basically if statements to basically only have a source term in kind of a small region of space in your domain. Okay, so I don't want the source term everywhere. I just want the source term in just kind of a small region. And I basically tell you where that region is down here. But you need to implement an if statement to help you out with that. Okay, so that's something that's new. Okay. And so the next thing is boundary conditions and convection velocities that change with time, right? And so as you can tell from the video, the windows aren't going to be open at first. And so actually at first, while the gas is just spreading, there's going to be no convection velocities in the domain at all. It's only after a certain amount of time has passed that you have that window open and you have your convection velocities. And so the way we're going to model that is we're going to have boundary conditions and convection velocities that change with time. And so once again, if you're going to have to use if statements here, and you're going to have to, have an if trigger, once the time has passed a certain point, only then will you, open the window and change the convection velocity. And so that's something new, okay? All right, and so this third point here, and this probably might be the most challenging part, is that I'm going to have you guys deal with the issue of cross-stream diffusion. Right? And so if you remember, cross-stream diffusion is something that happens when you have convection velocities that don't align with the grid. And so that's going to happen in this project as well, because once the second window is open, you're going to have velocities that are going down and across, and so ultimately it's going to be diagonal. And so if you use just kind of a basic finite difference scheme, or with finite volumes, we do a basic base interpolation scheme, that's going to result in some cross-stream diffusion. And so you can address this by upgrading your convection term. And so instead of using just the basic central difference, what you can do is you can use a higher order scheme. And for finite differences, you need to use a scheme that's at least third order accurate. And then for finite volumes, you need to implement what's called the quick scheme. Okay. And so this is something we'll cover, after we kind of do the basics of finite volumes. And so, this part of the project, you won't be able to do until later. But the first two parts and the majority of it you can already do. But this one you're going to have to wait until a bit later to know how to do that. Yeah. Okay. And in terms of the time stepping, we've gone over explicit Euler and implicit Euler to do your unsteadiness, but I want you guys to do implicit Euler for this system. Okay. And that's mostly just for stability reasons, because once the window's open, the convection velocities do get a little bit high. And so, it tends to go unstable if you use explicit Euler. So I want you to use implicit Euler with a time step of basically 5 milliseconds here, so 0.005. And I want you to simulate it for 400 total time steps so that the total amount of time that you're simulating is about 2 seconds, okay? And so these have already kind of been implemented in the starter code for you. And so I'm just kind of letting you know for that, okay? All right, any questions on the final project so far? Question, so for undergrads, can you get extra credit if we attempt both methods? Yeah, sure. So I'll give you up to 10% extra credit if you do both methods. Yeah. Mm-hmm. Yeah, I don't anticipate this class is going to be graded on a curve at all, because everyone's been doing pretty well so far, and so I don't mind giving a little bit extra credit for the undergrads for if you do both methods. Yeah. Mm-hmm. Okay. And so that's all the requirements, and so basically from here I have in this next section here are kind of the steps that I suggest that you follow to kind of complete the project. And so at first when you look at this project, it kind of seems like a lot of code implementing to do, and so I've kind of broken this down into a few steps where you can kind of just take it kind of step by step. Okay, and so if you follow these steps here and you kind of implement just kind of one thing at a time, it'll help you kind of break down this kind of big coding project. Okay? All right, so the first step is to just simply download the starter code. And so let me actually show you where the starter code is located. And so if you go to our class website here, okay, and so you can see this is our Canvas site for EGME 417. If you go to the file section, and then you go to the folder for project, okay, and under here you can basically see that I have the specs here. And so this document that I'm reading to you, you can download that and read it yourself. And then here's the starter code here for the finite difference method. So I don't have the starter code yet for finite volumes, and so that's probably something I'll do over spring break. But if you want to get started with the code for finite difference, here's the starter code for you. Okay, and if you open up the starter code, let me do that right now. Okay, what you'll notice from the starter code is that there's a lot of sections where I've marked a comment called to do. Okay, and so basically the only places where you need to add code into the starter code are places where I've marked to do. And so anything that doesn't have to do, you can just leave it alone. And so I've already implemented for you and it works and you don't have to worry about it. And so the only places where you have to implement things are wherever there is to do, right? And so there's quite a few. And so it's not like there's a few of them, but I've put most of the skeleton, I've put most of the structure of the code in there for you. And I've basically limited to just the areas where you need to kind of show off your knowledge of finite differences or finite volumes, right? But I didn't want you guys fussing with the structure of the code or kind of formatting it or variable names. And so I've kind of done most of that kind of legwork for you. It's just basically just implementing your theory. That's what I want you to focus on. So only look in the sections of the code that say to do, and that's where I want you to implement things. Okay. Okay, but you're not limited to that, and so I'm not going to mark you down if you put code outside of the to do. But that's kind of where I suggest that you add code. But if you want to add additional variables and additional things to help you out, by all means definitely go for it. But at least for my solution, then that's the only places where I have code. And so basically the way that I made the starter code was I took my solution code and I just deleted a bunch of stuff that that I thought was important for you guys to implement, and I left a comment that I said to do. Yeah. All right. So how many lines of code does it take to typically finish this? Yeah. So Tyra's right. So it is more than 5 and less than 5 billion, but you should be able to finish it around 200 to 250 lines of code. And so the starter code is already about 140 lines, and so you can expect to write about 75 to 100 additional lines of code on top of it. Yeah. Okay. And so the next step that I suggest that you implement is to just implement the filling of the room. Okay. Yeah, so I think I said a couple thousand at the beginning of the semester, because I I said that like overall for the class. So overall, I think you're going to be writing around that much. But for just this project, it'll be about about that much. Yeah. Okay, and so the first part of the project, I suggest that you just implement just the filling of the room. And so basically, right when the gas starts to leak and right when it fills the room. And so this process here is just pure diffusion. And so you don't have to worry about convection at all. And so you don't have to fuss about that at all. And the diffusion constant that I want you to use is basically 0.175. Okay. And so the difficulty with this part is to implement your source term that's going to be spatially dependent. And so basically what I want you to do is, if the x coordinate in your domain is between 0.45 and 0.55, and if the y coordinate is between 0.15 and 0.25, then I want you to give a source term of 400. But everywhere else in the domain, I want you to have a source term of 0. Okay. And so basically, I want you to write an if statement that checks, the x and y coordinates for this, for this node, and only implement the source term, if that's the case. Yeah. And for testing purposes, I said, because, I know you guys are going to be running this code a lot, as you're testing stuff. When you're testing stuff, I would suggest that you change the nx and ny to something modest like 25. Because if you run it, I'll tell you what, for my own laptop, when I set it to 50 and 50, it takes my laptop about 2 minutes to run the code, each time. And so, my laptop is, it's not the best one, so it is getting a little bit up there in years, but it's also no slouch because it can run games pretty well too. And so, if it's going to take you 2 minutes, every time to check whether your code is right or wrong, you're going to waste a lot of time just waiting for your code to run. But if you set the nx and ny to like 25, then you can, run the code and it goes a lot faster, and you can see something went wrong, much faster than before. And so I would wait until you feel like you're confident your code works before you bump up this nx and ny. I think for the result, I asked you to bump this up to 100 by 100. And so if you bump it up to 100 by 100, you can expect your code to run for a good 10, 15, 20 minutes, and you don't want to be waiting that long to get a solution. And so, only do the finer meshes, once you're kind of confident with that. Okay. All right. All right, question. So does MATLAB support something like get or input to get data from the user and keep the code running? I think it does, but I personally haven't experimented with that at all. And so you're definitely free to do that. I think especially Python. I think Python supports that really well. But I think MATLAB, I think it does, but I'm not 100% sure. Okay. Yeah. So for this initial run of the code, I was using finite differences, but I expect roughly the same performance with finite volumes as well. So last year, when I compared my finite difference and finite volume code, they were basically identical. So you can expect kind of the same performance either way. Yeah, that's true. Yeah, so if you want to, implement something fancy like Juan is describing, you can definitely do that as well. Okay, and so the first, after you have the filling part correct, then the next step is to implement, opening a window. And so when you open a window, 2 things are going to happen. And so the first thing that's going to happen is that you're going to have a convection velocity, and so you're going to change the u. You're going to change it from being 0 to this expression right here. Okay. And you're also going to implement a Neumann boundary that also varies in space. Okay. Because I only want the gas to escape through the window. I don't want gas to escape in other parts. I basically want you to make it so that you have a Neumann condition of 8, on this kind of small region where the window is. And 0 otherwise. Okay? And so basically the same methods that you use for this, you can use for this as well. Okay. And that method is if statement. So I'm kind of giving you guys a hint for that. Okay. All right. And then once you have the first window open, you can then implement the second window, and the second window is kind of more the same thing. And so you're going to activate a y velocity, and you're going to activate a Neumann condition for that as well. Okay. And then once you've implemented that, steps 1 through 4, you should have a relatively well-working code. And so your result should look very similar to what I have for this video right here. Right? And then once you have that going, then you can proceed to step 5, where you implement the higher order convection scheme. Where again, we're going to go over that kind of later in the class. Okay. And then once you're confident that you have everything working, then you can start to work on the deliverables, which is producing a bunch of the solution plots. Okay. And so for this, for this project, I'm basically, once you have the code written, then, I have you basically run the code under a lot of different configurations, and then compare the result and comment on the result. Okay? And then the last step is write the report, and then you can have an 8th step here if you want to profit, or whatever you do after the semester. Okay. Okay. So are there any steps or any questions so far on the steps to complete the final project? Okay. All right, so let's talk deliverables. And so what do I expect you to have in your final report? Okay. And so the format for the final report is going to be very similar to like a technical lab report or something, that you might have written for another class, or if you've read research papers, that they all kind of follow the same format. And so a big part of your report is actually going to be the results section, where I want you guys to show me several plots. Okay. And so the first comparison that I want you to make is, once you have a working code, I want you to run the code with 3 different values of the diffusion coefficient. Okay. And so the default setting is to run the code with a diffusion coefficient of 0.175, but I want you to run the code with a lower diffusion coefficient and a higher one, and then show all 3 plots, and then comment on the on the results. Okay. And so for these, for the plots here, I'm not only looking to see that your plots are correct, but I'm actually more interested in what you say about the plots. Okay. And so, when you're preparing this part of your report, I want you to pay attention to what are the discussion questions I want you to answer under each of the reports. This is what I'm going to be mostly grading you on. Okay. Because the code's going to be one thing, if your code works, I can see that, and this is just running for different ones. But from these sections, this is where I really assess whether you really understood the concepts in the class. Okay. And so this first part, we've gone over this quite a lot already, but what do you expect to happen when you change the diffusion coefficient? And can you, compare, and looking at these different results, can you kind of explain what's going on based on what you understand for a diffusion? Okay. And so these discussion questions are really important. So I really want you guys to really dive deep into these, for the report. Okay. Okay. And so the next part of the code here, well, I guess I only have you go up to 75, is I want you to run your simulation under 3 different meshes. Okay. And so there's the coarse mesh, there's the medium mesh, and there's the fine mesh. Okay. And so the finest I want you to go is 75 by 75. But if your computer can handle it, and if you're brave enough, you can go up to 100 by 100, and you can even push it beyond that too, if you have faith in your computer's RAM, and you downloaded all the RAM that you can or whatever. And so you can push it as far as you can, but past a certain point, MATLAB will complain and say, I don't have enough memory for this. And so you can try to push it as much as you can. I think last year, someone pushed it as high as like 125 by 125 before their computer kind of finally gave up. Yeah. And so, you can feel free to push this as much as you can, but just be careful. I would say do this one last. Yeah. And just like before, I want you to take a screenshot of the ending, and I want you to really comment and discuss about what's going on in between these results. Okay. Can you become this cool? No, you cannot. I don't think so. And so that's why I recommend just stick with these. But if you want to push your computer, do it slowly. And so do 80 by 80, 85 by 85, 90 by 90. Up until hopefully you can catch it before your computer spontaneously combusts. Okay. Okay. All right. And so in part 3, I want you to this part is comparing your results between the convection schemes. And so I want you to compare your results when you have your basic central difference, which is what we've been using. And then I want you to compare your results when you use the higher order scheme as well. Okay. And then comment on these results. Okay. Do we get an A if my project, if your PC fries? If you do everything before your PC fries, sure, but you don't get any extra points for that. So please don't intentionally destroy your PC to get an A in this class. Okay. All All right, and so in part 4, what I want you to do here is I want you to mess with the convection velocities, okay? And so I want you to run your code where you change the convection velocities a little bit, okay? And so, you know, I'll leave this part up to you guys on how you want to change this. And so you can either lower the convection velocity, you can raise it, you can, you know, time it differently. And so, you know, this is kind of like a free thing for, you know, a free response for you guys. So you can kind of change the convection velocity how you want. But again, you know, I want you guys to, you know, talk about your results and you know, see what you get. And then 5th, you know, if you're taking this for graduate credit or if you're doing this for extra credit as an undergrad, I want you to compare your results with finite difference and finite volumes. Okay. And you know, when you're doing this, make sure you run the code under the same conditions. So you make sure all your parameters are the same, and I want you to compare the results. Okay. And so ideally, you know, your 2 results for finite difference and finite volume should look identical, if not extremely similar to each other, because you know you're simulating the same thing. But you know, if you do see any differences, you know, then you can go ahead and comment them. Okay. All right. And so, you know, once you have that, and once you've written up the report, I want you to submit both your MATLAB code and the report, of course, and I want you to submit a video as well. Okay. Do I have any work from last semester to show us? I think I have the reports from last year. So I think I can upload some example reports if you want to look at those and see, you know, what I kind of expect from the report. The code they worked on was obviously, you know, pretty different. You know, so I'm not going to upload their codes because I think that also kind of gives you a lot of hints for this one as well. But I can show you the reports and just to you know, just to give you some examples on what I'm looking for. Mm-hmm. Okay. And so here are the final report components. And so just like I mentioned, so you're going to have an introduction, a methodology section, a results, and a conclusion. Okay. And so a big part of the you know, of the report too is going to be your method section. Okay. And so, you know, if you're unfamiliar with this section in scientific reports, basically this is the section of the report where you describe, you know, what you did. Okay. And so, you know, I really want you guys to spend a lot of time on this methodology section. And I want you to write it from the perspective of like, you know, you're writing this report to kind of teach someone else about, you know, about finite differences of finite volumes. Okay. Because, you know, this is an elective class, and, you know, you're learning something that's pretty unique that a lot of your peers aren't getting a chance to learn. And so I want you to write this, you know, basically, you know, write this as if you were in my shoes, as if you were kind of teaching this to somebody new. Okay. And so, you know, really take the time and, you know, don't really take anything for granted. And so, you know, you should talk about concepts and kind of build them up, you know, as if you were trying to teach them for the first time. Okay. And so you can, you know, I would suggest, you know, you use a lot of the material from my lecture notes for these things, or lecture videos, to kind of help you write this, you know, section. It's mostly for the conceptual stuff. And so, you know, I don't want you to just paste your code here and just, you know, comment on that. You know, I want you to talk about the concept. So, you know, how do you, you know, what the heck is computational heat transfer? You know, what is this equation? What do the different terms represent? How do we discretize it? You know, what does a mesh mean? Things like, just kind of, you know, a lot of the basic questions that I think by now, you know, are pretty automatic for you guys, you know, but explain them kind of from scratch for someone that's not taking the class. And so, you know, you know, that's mostly what I'm be looking for in this section. So, you know, it should be a pretty meaty section, your methodology. Okay. And so, you know, and I know the question that's on everyone's minds is there, you know, a page requirement? And so there's no page requirement, because I know everyone kind of has a different writing style and stuff. And so I don't want to place limits on that. But, you know, generally what I see is that the report should be around 8 pages. And so, you know, depending on your writing style and how big your figures are, it might be less than that. But I had some people last year produce reports that were like, you know, 15, 16, 20 pages long. So that's totally fine too. Okay. And so, you know, I'll provide a template for your final report later on this semester, and I'll post some examples like I mentioned before to kind of help you out there as well. Okay. All right, teams. And so this is not a team project, and so this is individual. And so I want everyone to write their own code, and I want everyone to write their own report, more importantly. Okay. But, you know, with that said, you know, I would definitely encourage you to work together with your classmates in developing the code. And so, you know, if you're having difficulties, you're trying to debug an error, you know, make use of the Discord server, you know, talk to your peers in the class, and, you know, have people, you know, help you out with these issues. That I'm totally fine with. What I don't want is I don't want people copying and pasting each other's code, because then that's obviously wrong. Okay. So you can work together in developing your code, because everyone's ultimately working on kind of the same code, but I want everyone to write your own code. Okay. And how I'll know if everyone wrote their own code or not is going to be in the methodology section. Okay. And so if you just copy and pasted someone's code, it's going to be very obvious from the methodology section whether this is true or not, because the methodology is probably going to look copy and pasted from my lecture notes, and that's when I know then someone didn't write their own code and they didn't really understand what was going on. And so you can work together with people, work through your issues, debug, but make sure you're writing your own code and make sure you're really understanding things. It's going to help you out with the methodology. If you copy and paste the methodology, then turnitin.com will know, because I'm going to make you guys submit your reports through turnitin.com. Yeah. Mm-hmm. And also I'll know too, because it's there's only so many of you guys in the class, and it's kind of obvious when you guys copy and paste on the reports like that. Okay. Okay. And so we spent way more time than I thought talking about the final project, but it's there's a fair amount to do, not only in writing of the code, but in the report as well. So, if there's anything that you're struggling with for the project, don't hesitate to reach out. Remember, I'm a resource for you guys to use in this class. But, I want, because this is a tech elective, and I know for a lot of you guys, this probably is one of the last classes you take. I want this to be, something that's memorable, something that you can take away from this class. If you want to work on, CFD codes or, similar things later on, I want this to be something that you can show off to potential employers or to graduate school, to show that you really understand this stuff. Okay. Yes. Yeah. So last year, for the graduating seniors, I recorded just a brief video just to say, congratulations, and, I wish you all the best. And so definitely, I will do the same thing for you guys as well. Okay. And so that was a very in-depth explanation of the final report. I do not sing, no. And I'm not going to give you guys an opportunity to make me sing, because my experience is that if I say everyone has to get this, everyone has to do this, to make me sing, then my experience is that you guys will always do that, and so I'm not going to give you guys that opportunity. My singing is for the ears of my fiance only, so it's not for my students. Okay. So any questions on the final report before we resume with finite volumes? The cat can sing, yes, but I cannot. But she cannot do it on command. She has to be very hungry to do that. Okay. So I'll post the examples for the final report for the final project probably later tonight, and then you guys can go ahead and get started with that. All right, and so let's go ahead and go back to finite volumes. All right. So let's go back and jump in where we left off. All right. And so this set of lecture notes is lecture note 09, and this is Intro to the Finite Volume Method. All right. And so just like we mentioned, last time and throughout, the project specs, the finite volume method is just a different methodology to run computational simulations. Okay. And so up to this point in the class, we've covered finite difference and in pretty thorough detail. And so you're reasonably well equipped to do that. But finite difference, remember, is not the only game in town. And so there's actually way more methods than I can count. And so finite volumes is just another method that we can use to simulate things. Probably you're asking, why are we learning two different methods in this class? And the reason I do that is because, finite difference, I feel like conceptually is a little bit easier to it's a little bit easier to grasp onto initially, because, we're just literally just applying finite differences to a differential equation. Finite volumes has a little bit extra steps in order to actually get to the point of of an algebraic equation. But it actually has a lot of really nice properties compared to finite differences, especially when you're talking about computational fluid dynamics. Okay. And so kind of the analogy that I want you guys to think about, or kind of a concept from a previous class I think will help you with finite volumes, is to think about control volume analysis from fluids. Okay. And so if you remember anything about control volume analysis, the way it worked was that you had, fluid flow in a certain situation, okay? And then what you did was you kind of drew a volume, okay, that was contoured to the flow. Okay? And then from this control volume, what you did was you looked at things, like how much mass is passing through the control volume, okay? Things like how much mass passes through, how much momentum passes through, how much energy passes through, right? And so we kind of looked at, control volumes basically allowed us to look at fluid mechanics problems as kind of like an inlet, outlet, things that cross the boundary in a type of way. Okay? And so i.e., or in other words, we're interested in things that cross the boundary of our control volume. Okay. And so that's kind of like the mindset that I want you guys to keep in mind as we go through control volume analysis, because it's kind of the same thing. And so in control volumes, basically what we're going to do is that after we kind of discretize our domain, and so we kind of break it up into a bunch of cells, the way that we're going to formulate our equations is to think about, what are some mechanisms that make our substance cross the borders of our cells. Okay. All right. And so let's talk about a mathematical tool that kind of helps us, deal with this, which is something that we actually used in fluids too. Whether you actually remember, whether the professor actually went over this or not is kind of not important. But this was part of it, okay? And that was the divergence theorem. Okay. And so the divergence theorem is a mathematical theorem, and so you might have learned this in one of your previous math classes. Okay. And so, we're going to use that here to help us out with this thing, okay? Because if you remember from last time, one of the hallmarks of the control volume method is that once we have our control volumes, established, what we can do on these control volumes is we can integrate over this volume. Okay? Right? And so, what you'll see is that once we kind of bring back our general conservation equation, we can perform an integral over the cell of that, over that finite amount of space. Okay. And so what the divergence theorem allows us to do is it allows us to convert integrals from one form to another. And the divergence theorem takes different forms depending on your what and how many spatial dimensions that you have. Okay, and so I'll show you the forms for 3D, 2D, and 1D. But they all, even though mathematically they might look pretty different, but they all kind of have the same idea. And so yes, yeah. So Ronald commented it's kind of the same thing as Green's and Stokes' theorem as well. Right? So it's kind of the same idea. But whether you're in 3D, 2D, or 1D, they all kind of have the same purpose. We want to transform a integral over a region. Okay, so I'll call this a region integral. And then what we're converting it to instead is an integral over the boundary. Okay. Okay. And so schematically, you can think of it like this, right? And so if I look at this control volume here, right? And so in orange, what I'm highlighting here is the region. You can kind of think of that, right? And so, one way that we can integrate a quantity is we can integrate over the entire, region that our cell takes up. Okay. But sometimes, that might be difficult to do, based on, the mathematical formulation of the integrand. And so what we can do instead is instead of integrating over the entire region, what we can do is we can perform an integral over just the boundaries. Okay. And that usually has some better properties and might be a little bit easier to do. Okay. And so the divergence theorem basically gives us the tool to convert these two types of integrals. Okay. All right. Any questions on this so far? Okay. All right. And so of course, I'm not going to go through the proof of the divergence theorem because you've probably already seen that in a previous math class. And honestly, I've forgotten it too. So, it wouldn't do us any good for me to be confused for the next 25 minutes. And so let me just give you the final forms for these. Okay. And so let's look at the 3D version first, even though we're not going to use it in this class. But this is probably the form of divergence theorem you might have seen in like a physics class or a math class. Okay. All right. And so on one side, you're going to have a triple integral. And you're going to have the triple integral of the divergence of u. Okay. And so if you've never seen this kind of upside down triangle before, basically this is called nabla. Okay. And what it is basically something that looks like this. And so it's kind of like a pseudo vector. And so it's basically a pseudo vector with partial derivatives in every direction. And so when you take the dot product in between nabla and u, you're basically taking the partial derivatives in every direction and then adding them all up together. The integral is over v. Yes. Yeah. So v stands for volume. Mm-hmm. All right. And so what you can do is by divergence theorem is you can convert this into a surface integral. Okay. And so if you notice, the kind of the notations here that, that people have already commented on. And so when I have just V by itself, what I mean is, the entire volume of the domain. When I use this kind of partial V right here, what I mean by this is the boundary of our domain. Okay? And I use V here to denote volume. Okay. And so this is the 3D form of the divergence theorem. And so we're not going to use this in this class because we don't do 3D simulations. That's a little bit too much for MATLAB to handle. But you can see that it kind of follows the same trend that I talked about on the previous page, right? And so on one side of this equation with the triple integral, we have a integral over a 3D region. Okay. Okay. Because when you do a triple integral, you're doing an integral over an entire piece of 3D space. Okay. And then by divergence theorem, we're converting this into a boundary integral. Okay. And so you kind of have to think about, your kind of spatial reasoning here. And so if you have kind of a 3D object, okay, so let's say that you have like a mouse, okay. And so, what's the boundary of a 3D object? And so the boundary of a 3D object is the 2D surface that kind of encapsulates it, right? So you can imagine, just wrapping it with like plastic wrap or tinfoil, right? And so the boundary, basically the boundary of something is one dimension lower than whatever that something is. And that's the very scientific explanation of that, right? And so, for 3D objects, one dimension down from 3D is 2D. And so the boundary basically is basically 2D surface. Okay. And that's going to extrapolate to, you know, once we go over the 2D form, which is the one we're going to be using for most of this class, and also the 1D form for that as well. Okay. Okay. Any questions on this? Okay. All right. So that's the 3D form of divergence theorem. And let's go over the 2D form. Okay. And so the 2D form, you know, we're just going to basically knock off one integral from everything above, right? And so the 2D form, we're going to have a double integral. Okay. And the domain for this double integral is going to be over an area. Okay. And so I'm going to give an A right there. And then the integrand is going to be the divergence of u dA. Okay. And it's going to be equal to a line integral of u dot n dA. Okay. Right. And so this integral on the right here, oh, let me do the thing. Okay. And so this is going to be on the boundary of A. And this guy right here is a line integral. Okay. And so this is the form of the divergence equation, or divergence theorem, that we'll use most often in this class, because it's, you know, we work mostly with 2D domains. Okay. And it allows us to perform this conversion of a double integral to a boundary integral. Okay. And I'll visually kind of show you what that means on the next page. But are there any questions on this before I turn that page? Okay. Okay, and so, you know, by divergence theorem, basically we're doing this. Right? And so instead of integrating over a 2D domain, which is what we have here, okay. And so when you perform a 2D integral, a double integral over a, you know, a 2D domain, basically you're integrating over this entire space, right? So this is double integral over 2D domain. Okay. And instead, what we're doing is just a line integral around the boundary. Okay. And so instead, we're going to perform the integral basically just on these lines right here. And then actually what we're going to do is, because, you know, because we have sharp corners here, it's a little bit hard for, you know, the line integral to go around sharp corners. And so we're going to break this up into 4 separate boundary integrals. Okay. And so what you'll see later on, you know, once we start doing diffusion and things like that, you know, we're going to end up with 4 different boundary integrals around each of our cells. Okay. All right. So that's just kind of a visual aid to kind of show you what the divergence theorem is doing. Okay. And then finally, let's go over the 1D form of divergence theorem, which doesn't actually have a name because, you know, it's actually very obvious. Okay. Okay. And so the 1D version of divergence theorem is basically just performing the integral. Okay. And so if you have the integral of the derivative of a function, and so you have integral of d phi dx, what this is equal to is just simply phi of b minus phi of a. Okay. Right. And so it's kind of trivial from that. And so, you know, even though this one might seem kind of obvious, you know, it still follows the same trend as before, right? And so on the left-hand side, we have an integral over an entire 1D domain. And so this is kind of like our region integral. Okay. And on the right side here, we have our boundary terms. And so, you know, the boundary for the boundaries of a 1D domain are just, you know, 2 points. And so, you know, we just evaluate our function at those 2 points. Right. And so, you know, it looks easy, but, you know, it still follows the same trends as before. Okay. Yeah, that's the fundamental theorem of calculus. Yep, that is true. All right. Any questions on divergence theorem? Okay. And so, we'll use divergence theorem quite a bit in order to evaluate our, our integrals, or transform our integrals, I should say. And so the next thing I want to go over is what's known as the trapezoidal integration rule. Okay. All right. And so, I know like all these talks of integrals are, it seems a little bit intimidating compared to, finite differences. We didn't have to do this. But the good news is, we're never actually going to perform any integrals. Okay. All right. Oh, did I? Oh, I see. Okay. So the good thing is, we're never actually going to perform any integrals. And so we're just going to simply, approximate them. Okay. So the trapezoidal rule is a way to approximate integrals without actually performing integration. Right? Because we've already kind of talked about how like computers can't solve differential equations, and so computers also can't integrate stuff. And so before you say Wolfram Alpha exists and stuff like that, yes, I know that stuff exists, but your MATLAB just out of the box right now can't perform integration, and so you kind of need to help it out here a bit. Okay. All right. Yes. And so basically the way that we're going to do this is we're going to approximate an integral using basically the centroid of a domain. Okay. And so let me show you how it works in 3D. And then, I'll show you kind of the 2D and 1D versions. Okay. All right. And so in 3D, we have the following. Okay. And so let's say that we have a triple integral over a volume domain like that. Okay. And we want to integrate this function. Okay. But we actually don't want to perform a triple integral because that's a pain in the butt. And so basically what we can do is we can take the integrand and evaluate it at the centroid of the domain, and then we multiply it by v, okay, where v is the volume. And so there's two parts of this. And so this first part here is the integrand evaluated at the centroid of the domain. Okay. And then this v right here, this is simply just the volume of the domain. Okay. And so you actually don't have to perform any antiderivatives at all. You just take the integrand, evaluate it at the centroid, and then multiply it by the volume. Okay. Let's see. Yeah, there's actually multi-dimensional versions of trapezoidal and Simpson's rules. It's just, Simpson's rule gets a little bit more complicated. And so, just for this class, the only thing that we really need is just trapezoidal rule, because it's the simplest to do and it's the simplest to evaluate. Because you're going to be coding these up end of the day. And so it's a little bit easier to do this, when you combine it with all the other stuff that we're going to do. They exist out there. They're just a little bit trickier and a little bit more painful to implement. Okay. All right, and so that's the 3D version, but of course, there's 2D and 1D versions as well. Okay, so the 2D version. So 2D, we're going to take a double integral, and so this double integral can be, a classic double integral, or it can be a surface integral. Okay. And so we can approximate this by evaluating the integrand at the centroid. Okay, so we have f of xc and yc, and we multiply by not the volume this time, but the area. Okay, so it's the same idea. And so all we have to do is basically just take the integrand, We don't have to take the antiderivative or anything like that. Evaluate it at the centroid and then multiply it by the area. Okay. All right. Any questions on this? Okay. All right. And so I'll show you the 1D case, and we'll do an example for this just to kind of prove to you that it works, because I think the initial reaction when you see this is that, you know, there's no way that works. Otherwise, they would have taught us this in math. And so this is kind of like one of those, you know, secrets that the math department doesn't want you to know, right? At the risk of sounding like clickbait articles, but it's you know, it works pretty well for most cases. Yeah, yeah, math teachers do hate me. Yeah. Yeah, so to get V and A, you would have to do it by geometry. Yeah, but most of the times you're working with pretty, you know, standard shapes. And so for our finite volume method, you know, you're going to work with on square domains. And so taking the area of a square is usually pretty easy. Okay. And so in 1D, we basically just have this, right? And sort of instead of actually taking the antiderivative of this, what we can do is we can evaluate this at the centroid, okay? And then multiply by the length of the domain, which is B minus A, okay? And in 1D, XC is actually pretty easy to determine. And so in 1D, XC is just going to be B plus A divided by 2. Okay, and so just what is just literally just the middle of those two stuff. Okay. All right, and so let's do an example just to prove to you that this works, and you know why it's kind of a cheat code in a way. All right, and so let's take this integral here. So let's take the integral from 6 to 10 of simple function, so 4x plus 6 dx, okay? And let's evaluate this using trapezoidal rule, and then let's evaluate it also with normal integrals just to show you that it works, okay? All right, so let's use trapezoidal rule first. And so for trapezoidal rule, we need two things, and so we need the centroid. Okay, and so the centroid here is just going to be whatever's in the middle of 10 and 6, and so we have 10 plus 6 divided by 2 is equal to 8, okay? And we also need the length of the domain, which is going to be 10 minus 6, which is going to be 4, okay? And so let's evaluate our integrand at the centroid. Okay. And so our integrand in this case is 4x plus 6. And so we're going to plug in 8 in for x. Okay. Now so we have 4 times 8 plus 6. And this is equal to 38. Okay. And then we're going to multiply 38 by the length of the domain, which is 4. Okay. And so we have 38 times 4, and this is equal to 152. Okay. Right. And so that's the integral from using the trapezoidal rule without actually having to perform any integral stuff. Okay. Yeah, you might have picked this up in another class too. So you know this might probably not be maybe not the first time you've learned trapezoidal rule integration. And so it's almost like a very bastardized form of Riemann sums. And so I'm not sure how they teach integrals nowadays, but Riemann sums was kind of the very first thing that I learned to perform integrals. And so this is kind of like a very, very simplified version of Riemann sums. You can think of it like that. Yeah. But also extrapolated to 2D and 3D as well. All right, any questions on this where we evaluate the integral the normal way? Okay, so just to prove to you that it works, if you haven't done so already, let's evaluate this integral, you know, the normal math way. Okay. Right, and so we have integral from 6 to 10 of 4x plus 6. Okay, and so if we perform the antiderivative of the integrand, we have 2x squared plus 6x, and we're going to evaluate this from 6 to 10. Okay. And so we plug that in, we have 2 times 10 squared plus 6 times 10 minus 2 times 6 squared minus 6 times 6. Okay. And so we plug all this in and we get 152. And then, you know, just like that, you know, we get the same thing. So, you know, just to prove to you guys that it works. Okay. All right. And so that's the trapezoidal rule. And so, you know, finite volumes, I know it involves a lot of integrals, but, you know, we don't actually evaluate them. And so we usually just use trapezoidal rule to do that for us. Okay. Okay. Any questions on this? Okay. And so, you know, now that we've looked at, you know, all the mathematical tools that we need, and so we've gone over divergence theorem and we've gone over trapezoidal rule. Let's see how we actually implement this into the finite volume method. Yeah, I'll check out the video afterwards. I don't mind the memes at all. I actually enjoy them quite a bit. But let me finish up this last point and then I'll check out the video. Okay. All right, and so we've talked about, you know, all these different integral rules and all this stuff, but ultimately, you know, we want to solve our conservation equation, right? And so I'm actually going to put our conservation equation in a slightly different form. So I'm going to put it in vector form, just because it's going to be a little bit easier for us to apply our rules. Okay, but it's going to have all the same thing. It's just going to be in different forms. All right, so first we have d phi dt plus divergence of this. Okay, and that's going to be our convection term. Next, we have divergence of k, gradient of phi, okay, plus q. Okay. And so I know this looks very different from our usual equation, but you know, I assure you all of our usual suspects are here. And if you actually you know, evaluate this out, you get our conservation equation in our old form. Okay, so let me go ahead and label these terms. Right. So of course, you know, our time derivative term, that's our unsteady term. Then we have our convection term. Then we have our diffusion term. Then of course we have our source. Okay. Right. And so it looks very different here, but you know, I put it in this form so that we can apply divergence theorem, you know, a lot easier here. Okay. All right. And so just like we did with finite differences, we're going to first consider a steady case. Okay? And so for the steady case, you know, we're just going to ignore the unsteady term for now, and we're just going to consider these guys right here. Okay. All right. And so now that we have the equation in this form right here, the steady form equation, let's kind of remember that, you know, with finite volumes, we're considering, you know, these equations over a cell. Okay. And so let's take these equations and let's integrate them over a cell. And then after we perform integration, then we can apply some of the rules that we went over, you know, previously. Okay. Any questions on this? Okay. Kaiser Soze. What is that? Was it something weird that I wrote down? Okay. Okay, and so after we perform the integral, we have the following expression. And so first we have the integral over our convection term. Okay. And so since we're doing we're going to assume we're in 2D for now. And since we're in 2D, we have a double integral here. And so our double integral is going to be double integral of the divergence of v phi, okay, dA. And this is equal to the double integral over the area of our diffusion term. Okay, dA plus the double integral of our source term. dA, okay? All right. And so that's, that's what we get just by simply integrating our governing equations, okay? And so now let's take some of these integrals and transform them into boundary integrals using the divergence theorem. Okay, and so in particular, I'm looking at the convection integral and also the diffusion integral. Okay, and so let's convert these into integrals over our boundary instead. Okay, and so let me go write that down first, and then we'll end there for today. And so for our convection integral, we have the following. And so we have a line integral over the boundary of phi v dot n ds, okay? And then we have a line integral over the boundary of our diffusion term. And so our diffusion term is going to be k gradient of phi dot n ds. Okay. And then for the source term, since it doesn't have a divergence in there, we're going to leave that alone. And so we're just going to have double integral of q of xy dA over a. Okay. And then this right here, this is basically our finite volume expression for convection diffusion in 2D. Okay. All right. And so next time what we'll do is, I'll show you exactly how these integrals break up, and then we'll start to actually apply it to our diffusion equation, okay? And so from here, our class is going to progress kind of in the same way that we did for finite differences. And so, first we're going to consider just diffusion, then we'll bring convection into the fold, and then we'll cover unsteadiness after that, okay? So it's kind of almost like deja vu of what we've kind of done before, okay? All right, so thank you guys for tuning in today. I know it's the last week before break, and so it's always kind of the hardest week to come to class, especially I know when you guys are busy with midterms. So, I really appreciate you guys coming to class and staying all this time. And so, hope everyone has a good evening. Best of luck if you have midterms this week. I'll see you guys on Wednesday.
Thank you, Professor.
Thanks, guys. All right, let me check out the video. Oh, this meme. I'm about to end this man's whole career. Yeah, I've seen it before. Yeah. It's a little bit old at this point. This is one of the first ones that got really big, I think, right? Where it came out quite a while ago. But it's a good one. Yeah, I'm old too. All right. See you Wednesday.